Hello everyone, welcome. Welcome to another day of solving Advent of Code. Today is day 10, so that's what we're going to do. We're going to be solving day 10 of Advent of Code. Hey there, Paramesh. And when we're done, hopefully we finish this early enough that we'll go back to day 9, because as you might see, I haven't solved part 2 of day 9 yet. I know what I want to do, but I haven't done it yet. So we will probably take care of that after we get through day 10. Hey Roger, hey Angie, how's everyone doing today? As everyone knows, as per usual, if you have at any point if you have any questions, any remarks, feel free to share them in the chat. Alright, let's get started. Let's open day 10. For part 1, sorry, let me just update this in the corner. Alright. Yeah, there's only 2 more days, which is at the same time a shame, but also, like you say, yeah, it's good that there's only 2 more days, because this has been pretty tiring, especially yesterday and today. Pretty tough days, I felt. Hello T2, how are you doing today? Well, completely unrelated and irrelevant, but the person that got me into Python was called Tito. Yeah, the last 2 were brutal. Alright, well, hopefully, or thankfully, today wasn't that terrible. It's just, well, you'll see. So let's start with part 1. Let's start from the beginning. For part 1, you're going to take your input, which is a bunch of lines that look like this. You're going to ignore the final section with the braces, and so you just look at the square brackets with the dots and the octothorpes, or the pound signs, and the numbers inside parentheses. Now, inside the square brackets, you have the representation of a system of lights or light bulbs, and you have 4 light bulbs in a row, and the 2 pound signs say that you want to flip some switches until only the 2 central lights are on. Now, the thing is, the switches you have are given by the numbers in parentheses, and each switch flips the state of the light bulbs inside the parentheses. So the very first switch flips the light bulb with index 3, which is the last one. The second switch flips simultaneously light bulbs 1 and 3. This switch flips only the light bulb with index 2, etc. So most switches will flip the state of 2 or more light bulbs, and you have to figure out the minimum amount of switches you need to flip to get the light bulbs in the state that is indicated. Now, throughout the whole event, I've been waiting for a problem like this, where you can model the problem as a graph problem. Now, this isn't necessarily the best solution, because if you think about it, you can figure out an even better solution. But one way to think about this is, you start with this empty state, and now each switch represents a change in state. So the switch just 3 is this dot 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 pound, and this is the switch 3. The switch 1 3 will flip 2 light bulbs, so it's going to flip light bulbs 1 and 3, and this is switch 1 3. And then you could think, alright, this is a 3. If I'm in this state, and if I flip switch 3, I end up like this. So I have the pound sign, I have a light bulb on, and then the 2 are off. But if I'm in this position and if I flip switch 1, 3, I end up in the same place. And I'll stop, don't worry, I'm not going to draw the full diagram. What I'm trying to show is that you can look at these states and the changes of the states as a graph. And I have been waiting the full event for a problem like this, so when I read the problem, I immediately thought of this. Again, not necessarily the very best idea, but it's decent. And because we want the least number of switch flips, the way we're going to explore this graph and explore these paths looking for the targets is with a breadth first search, which essentially means first we look at the states that are one change away, because there's going to be other arrows here that I didn't draw. There's other state changes here. And you look in this ring of distance 1 and you see if the wanted state is there. If it's not, you widen your search to look at the section of states that you can get to with 2 moves only, such as this one. And there's going to be other places you can get to. I didn't draw the whole thing, but there's going to be plenty of these. And you keep going until you find your target. And because you're doing this in order, going from inside out, you'll know that you will find the target in the least amount of switch flips. So you're guaranteed to do that. So that's how you can solve part 1. Let me know, I know there's folks watching that have solved this already, let me know if you did something similar or not, because again, this isn't necessarily the very best idea, and I was primed to think of this, so that's why I ended up doing this. Let's save the file, the input file. And now let's open the editor. Alright, so how do we do this? Well, the first thing we're going to do is we're going to parse our input. Now for that, what we want to do is we want to go through the lines. And for each line, let me show you the input again. For each line, we're going to split the line into 3 sections. The first section, which contains the target state, the middle section, which contains all of the light switches, or all of the way these things are connected, and the final one is something we're going to ignore, because for part 1 you don't need it. Roger says, no idea how to start. Well, brute forcing your way out of this is always a good idea, or a good first idea. Brute force would probably work here. I mean, my solution isn't that different from brute force. So now, what are we going to call these? One machine per line. So we're going to have a list of machines, and for each line, we take the target, we take the buttons, or the switches, or whatever you want to call them, and you ignore the last section, and you split the line. So all of the switches in the middle are going to end up in this list. The target is in the beginning, and the last thing inside the curly braces, we ignore it. Now for the target, let's do... It's easier to work with a list of booleans instead of a list with dots and pounds, or pound signs, because you can easily flip a boolean with not B. So that's going to flip between true and false for on and off. So the target becomes the character matches the pound sign for character in targets. Dot split. So what am I doing? target is a string that starts and ends with square brackets. We get rid of the square brackets, and now we iterate through the remaining string. Oh, I don't need to split. Let's get rid of that. I iterate through the remaining string, and I compare with the pound sign. If it matches the pound sign, we get a true because we want that light bulb to be on. Otherwise, we get a false. For the switches, we're going to go through each switch, ignore the parentheses, split on the commas, and turn these things into integers. So the switches are what? Like, given a switch, you want to ignore the parentheses, we want to split on the comma, and we want to map the built-in integer over the results. And let's turn this into a tuple. We want a tuple with this information. And when we're done, we can return, then we get the target and the switches, we add that to the machines, the targets and the switches, and once we're done, we return the whole thing. Now to solve part 1, given some machines, we're going to use breadth first search. So for each target and switches in machines, we need to set up a depth first search for the targets given our starting position, which is, according to the problem statement, all false. So the start is all light bulbs are off, and we have as many light bulbs as the length of the target. This is our starting point, and now what we need to do is we need to explore this graph. As we explore, to avoid visiting states more than once, because we know that there's different paths that go there, we're going to keep track of all states we already visited. And because we can't do this exploration in all directions at the same time, we're also going to keep track of a queue of positions we want to explore next. So in the beginning, we start with the, starting position, and then we check, okay, there's a couple of positions around us that we want to check next, and we add those to a deck, and then we go through each one of those one at a time, figuring out what are the positions that we're going to check next. Alright, so we need a deck to keep track of the positions to check next, and a set to keep track of everything that's been visited already, to avoid duplicated work. Visited. Alright. So the visited is a set that starts with a starting point, and the queued for processing is a deck that starts with start. Now let's import deck from the module collections. And the reason we're using a deck instead of something like a list is because we want elements to come in and out in a FIFO order, which is first in, first out, which is what gives us the breadth first search. If we use something like a list to append and pop, we would get last in, first out, which would give us a depth first search. But we want breadth first. Now the standard loop for the breadth first search is a while loop. This could also be implemented recursively, for example, if you prefer that. But you're going to do, while there's queued states to visit, we're going to process one. So you grab a state from the queued deck. You're going to pop from the left. You're appending from the right, popping from the left, so that stuff that's been there the longest leaves first. And now, if the state matches the target, then you're done. And you want to increment the total, which is a running total you're keeping track of, which is what you want to count, the number of switches you need to flip. You're going to increment that by the total number of switches it took you to get to the target. But that's a piece of information you don't know, so you actually need to keep track of that in the queue or in the deck. So in the beginning, to get to the start, it took you 0 flips, and each time you put something in the queue, you're going to keep track of the number of switch flips it took you to get there. So this is a counter that's going to be incremented. So the number of steps it took me to get here. So the total increments by the number of steps and we stop. Otherwise, if we didn't reach the target, we're going to go through each switch we have and we're going to check what's the state we get to if we start at this state and use this switch. So how do we do that? So the next state, or the new state, is built by doing what? You're going to take your... how do you do this? So switch is indices that need to be flipped. Alright, so you're going to say not S if the index is in the switch, else S. These parentheses are redundant, but I think they will make it slightly easier to read this. And now we go through each index and S in the enumeration of the state. So we go through each Boolean value in our state, which is S, and we also enumerate those to get the index, and then we check if this index must be switched, because if it must be switched, then we switch it or we flip it, otherwise we leave it, we just let it be. So this is our new state. Now we want to queue this, we want to queue this to be processed later if it hasn't been visited yet. So if new state not in visited, then we queue it for later. So queue.append this new state and its updated number of steps. So if it took us this much steps to get to the current state, then the new state is one more away, or the number of steps is one more than whatever it took us to get to the current state. And we also mark this as visited to avoid adding it twice to the deck. And I think that's it. And when we're done, we return the total. So now we parse our input. And we print part 1. Let's see how spectacularly this breaks. Unexpected for switch. Oh, I don't even know how to write code. Where's for switch for switches? Line 12. For switching switches, the 12 I got a 0, which is clearly wrong. How did I get the targets? Alright. So now we start with everything off. If the state matches the target, we stop. New state is... Come on, this shouldn't be a problem. Let me think. So we start with everything off. And in the beginning, we've seen the starting point. All right. Now we grab a new state to process. And if it's the target, we stop. All right. If it's not the target, we need to try building these new states. So for each switch, yeah, this is kind of weird. Let me print my machines just to make sure I'm parsing the input correctly. But it looks like I am. All right, true, false. Fine. So now let's grab the sample input. Let's put it here. And let's try working with a sample. So now we run and we see the false, true, true, false, which is the first one. Alright, so the input is being parsed correctly. Now we troubleshoot our breadth first search. So while queued, let's add a breakpoint here. Let's run this. Now we print the target, which is the very first target, and we print the switches. Alright, so this looks okay. So now let's trace through a couple of lines of code so that we get inside the loop. Alright, so the queued should have a single, now that it's defined, it should have the single starting point. And now we should go through the switches and we should build the new state. So let's take a look at this new state. Alright, we're inside the list comprehension. Alright, so the new state has been defined. False, 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 true. What's the switch like? Yes, so the switch updated the new state correctly. And visited shouldn't have this new state. So you should go in and you should append this new state to be processed. And visitor should get this new. Okay, so now what's queued? Okay. So now you keep going. You define the new states. Now let's print the switch. So I flipped 1 and 3. So now if I print my new state, it should be false, true, false, true. Alright, so the update of the states looks okay. In which case, why does it feel like it's never hitting the target? It looks like it's breaking out of this loop because the deck empties itself, which doesn't make a lot of sense. So let me do else print queue is empty. So now we leave the debugger. Let's not stop there for a second. Queue is empty. So it emptied out the queue, which is weird. So now let me print all of the visited states. This was stupid. What I want to do is print. Oh no, I can't believe it. Could it be that the target is a list? Yes. Of course, and the tuple is never the same as a list, so that's why I was failing. That's stupid. Alright, and now I get the 7, which is the correct answer for the sample, I believe. Is it? Where's the sample? Yes. Alright, so for the sample, the result is 7. And for my input, it should be 491. So let's run this on my full input. And let's remove the... Well, these prints won't happen, so it's okay. 491. Alright, so it was just a silly mistake. I was trying to compare a list with a tuple. Which doesn't... I mean, it works, but it compares as false. What's the print that I'm making that I want to avoid? It's this one. Questions about part 1, folks. Let me know how you feel about this. Alright, if you think this is neat, wait until you see part 2. No, just kidding, part 2 is going to be painful. Alright, so part 2 is similar but different, but similar, but different. For part 2, you're going to look at the buttons and the way they affect the light bulbs, but now you look at the right part of the input, and the right part tells you... Wait, what does this tell you? Right, counters. Now it's not, you're not switching light bulbs, you're not switching light bulbs on and off. Now you're incrementing counters. So the parenthesis 3 increment the counter 3. The second button increments counters 1 and 3. The third button increments counter 2. The fourth button increments counters 2 and 3, etc. And what the result tells you is your target values for the counters. Yeah, Tiro says you knew you had to track multiple objects. The problem was how. Yeah, I mean the graph solution with the breadth first search is just one way. There's a couple of others, but yeah, you do need to do the bookkeeping correctly. Otherwise it becomes either messy or impossible. And now this right part of your input tells you the value you want in each counter. And you can only press each button an integer number of times, and 0 or more times, right? There's no way you can press a button -2 times. So the question now is, what's the fewest button presses you need to get to the target values for the counters? This is the question you need to answer. And this one can also be seen as a graph problem, except instead of light bulbs that go on and off, you're talking about counters. The problem is, in your real input, you have very large numbers. Let's see if I can find some of the really large ones. So for example, this one you have, and this isn't even one of the largest ones, but you have 7 counters, and some of them need to go higher than 100. And there's a couple of other that are worse. So this is a very, very, very large problem. And I was trying to do this with a graph algorithm with A star, which is a nice algorithm to find shortest paths inside the graph with a heuristic to try and optimize the searching so that you're as clever as possible. And my solution just didn't finish. It was taking forever and ever to run. So this didn't work. A graph solution that's somewhat similar to the one I drew for part 1. But you can do something else, which is very efficient, works really well. I found it a little bit less satisfying, but it still works. So I'm just opening my notebook because I don't want to mess this up. But let's see if I can explain this to you. So you have, what is it? Your target for the sample input, let's focus on the sample input. Your target is 3, 5, 4, 7. This is your goal. You want to get here. And you have a couple of switches, which are the 3, the 1, 3, or a couple of buttons, whatever you want to call them, the 2, 3, 0, 2, and 0, 1. These are your switches. Now let's give them names, just to make it easier for us. So I'll call this one A, because if everything is a number, it's going to get very confusing really quickly. This is B, C, D, E, and F. Alright, so each button now has a letter. Now, let's focus on the first number of my result, the 3. regardless of the buttons I press, and regardless of however many times I press them, I need to make sure that the very first counter has the value 3. Now I can look at my buttons and ask myself, which of these buttons affect button 3 or affect counter 3? Well, it's only, let me swap colors, it's only E and F. So what you can write is E plus F must be 3. Here I'm using the names of the counters to represent also the number of times I'm going to press them. Alright, now you can look at the next counter, 5. What buttons influence counter 5? Well, only F and B. So what you can write is B plus F equals 5. This needs to happen. And now you keep going. Now you look at the 4, and you see that the third counter, which is counter with index 2, the counter with index 2, can be incremented with buttons C, D, and E. So you write C plus D plus E equals 4. And finally, you look at the fourth position, the 7, and you ask yourself, what are the buttons that increment this counter? Well, it's A, B, and also D. So you write A plus B plus D equals 7. So you know, whatever you do, you must satisfy these restrictions. And the other thing you know is that you want to minimize the number of button presses. So there might be different ways of getting here to these restrictions, but you want to do this in the minimum number of button presses, in the smallest number of button presses possible. So you want to minimize the total number of button presses. Now, as it so happens, this is a well-known type of problem in mathematics and in computer science. This is a linear integer programming. Wait, I never know the order. Integer linear programming. Integer linear programming. Yes, integer linear programming. All right. Sorry, I never know the order of the words there. But this is a well-known type of problem called an integer, or rather, let's start with linear programming problem. This is a linear programming problem, and in particular, you want all of these numbers to be integers because you can only press buttons an integer number of times. So this is how you can tackle your problem. We're going to use SciPy to solve this problem for us. Now, personally, I don't find this to be the most satisfying solution because whenever possible, for myself, I try to avoid third-party modules like SciPy, but sometimes it's just inevitable. I mean, you could implement a linear programming solver yourself instead of importing SciPys, and it's actually an interesting exercise, but I thought that for what I would get from it, it just made more sense to use SciPy. So this is what we're going to do and how we're going to solve the problem. And the most important step is figuring out these equations and figuring out how to write these from the input. So now, very quickly, let's see how SciPy can solve something like this. So there's a function in SciPy called milp for mixed integer linear programming. It's written here, and the documentation I'll paste the link in the chat in case you want to take a look at this. The documentation shows you this thing. Solve problems of the following form, and this is mathematical notation. But the way to read this is... Oh, they also show it with Python notation. Great. So the thing to realize here is that this min, this is the thing we want to do. We want to minimize something. And the x is the vector that represents all of our variables, which are the number of button presses. And the c is a vector that specifies the linear function we're trying to optimize. Apologies, my voice is acting up. So c times x represents the function we want to minimize, and x just represents the variables. Now, because what we want to do is just minimize their sum, our c is going to be a vector of ones, just ones. As many ones as variables. And then you can say, okay, let's minimize this. For us, it's the sum, such that, and now you get to write a bunch of different restrictions. You can write restrictions on the number of clicks, and for us, the only restriction is that the number of clicks must be, well, an integer, but that's already baked into the function, the MILP function, and also non-negative, so it has to be 0 or more. But by default, that's also the behavior. So where you see L less than or equal to X less than or equal to U, by default, the default behavior of this is ensure each variable is not negative. So we don't need to worry about this. We only need to worry about the BL and the BU. BL and BU. Now, BL less than or equal to AX less than or equal to BU is just a very short and convenient way of writing our equations. So for us, because we have equalities, we have that our BL, which stands for the lower bound, is going to be the same as our upper bound, which is the numbers to the right of the equal sign. So it's going to be 3, 5, which it's our target, 4, 7. This is our B. And then our A is extracted from the numbers multiplying the variables. So how do we get our A? Let me delete this. Let's say that this is what makes B. Now we're left with creating A out of these equations. How do we do that? Well, you start with the structure. You're going to create a matrix that has as many rows as equations. So we need 4 rows. And then you need as many columns as variables. I don't need this. You need as many columns as variables. Since we have 6 variables from A to F, you need 6 columns. So let's do this. Let me write it here. So A, B, C, D, E, F. You need 6 columns. I know these are not evenly spaced. Please let me be. And now what you do is you look for each row, you look for the variables that are mentioned. In this case, it's just E and F. So you do, wait, actually, am I doing this right? Let me think for a second. X is going to be the variables. Yeah, I'm doing this right. So you look at the first equation, EF. So you put a 1 on the E and the F, and everything else is 0. For the second equation, you have the B and the F. So B and F are 1, and everything else is 0. and you just repeat the process. C, D, E, so A and B are 0. C, D, E are 1 and F is 0. And for the final one, A and B are 1, C is 0, D is 1, E and F are 0. And this is your matrix A. And once you've built this, you can use SciPy's function. So the thing you need to be most careful of is the process of building the matrix A. Another way to look at it, since writing the equations can be a bit cumbersome, is going through each button and realizing that each button is a column. Look, this is button A with the 3. So you go to row 3, and the indices are 0 based, 0, 1, 2, 3. You go to row 3 and you put the 1 here. For button B, you see the 1 and the 3, so you put 1s in those positions, the 1 and the 3. So you can also go column by column. So there's two different ways of building the matrix. I think column by column will actually be easier than using the equations. Do you have any questions so far? Or does this make some sense? Or at least as much sense as it can make, if this is your first time hearing about linear programming? Now, in case you're still there, Anje, and sorry to put you on the spot, but if you're still there, and if you have a chance, can you just write 1 or 2 sentences about your Z3 solution? Because I know that's a set solver, but I don't know. For me, it's not immediate how you solve problems like this with Z3. So if you could just write 1 sentence, that would be super helpful. If not, that's okay. I can just look it up after. Alright, so now let's solve this with SciPy. The first thing I needed to do was actually add SciPy to my virtual environment. I did it with UV already. Now let's parse our input, because now we care about a different part of the input. So this was parse input P1. Now we're going to parse our input for part 2. Parse input P2. And the beginning is similar. But now we don't care about this target. The target now comes from the end. And this target has integers. So I want to take my target and ignore the curly braces, and then split on the commas, and then map the built-in integer over that, and then turn this into a tuple. So this is my target, and my switches, it's still the same thing. It can be a tuple with the integers. Alright, so this gives me my machines. Now I want to solve part 2. I need a running total, and now I'm going to go through each target and the switches in my machines. And now I need to build all of those vectors and matrices. So let me go back to the documentation, and let's look at the example provided with the function. So first we build the C, which for us is just as many ones as there are variables. And the variables are the number of switches. So C equals, now we need to import numpy, I forgot about that, so import numpy as np. Numpy.ones, now how many ones do we need? Well, as many switches as, we need as many ones as switches, and we want this to be an array of integers. Alright, C is done. Now for B, we just need the targets. So we turn the target into an array. And we also needed, what was it? So we have B, we have C. We need the matrix A. So first, we create A as a matrix that's all zeros, and then we fill in the ones as required. So let's start by building the larger structure. As many rows as there are counters, and as many columns as there are switches. So the number of rows is the number of, the number of counters, and the number of columns is the number of switches. And our matrix A is a matrix of zeros, with shape n rows, n calls, and we want our our zeros to be integers. And now we fill the matrix. So for each switch in switches, and we also need to know the index of that switch to know the index of the column we're modifying, because we're adding the ones per column. Now for the switch index in switch, so for the number in the switch, we go to A, to the correct row of the current column, and we set it to be a 1. So this right here corresponds to looking at the second switch, doing the 3 there, and saying, okay, we need to go to the second column, this one, to row ID 3, this one, and putting a 1 there. That's what we're doing, but we're doing this for all switches. So we have A, B, and C, and the example now shows that after you have A and the B's, for us they're the same, you create this linear constraint object from SciPy. So we need to import this. The linear constraint. You build the constraints. This is not something you make up, right? You read the documentation to figure out that's how you use the function. So I didn't make this up, I'm just following the documentation. I have my constraints. And then this integrality thing is just for you to specify whether you want your variables of the result to be integers or not. And we definitely want that. So we can actually copy this. And finally, you solve the problem by calling the appropriate function. So I also need to implement MILP. Sorry, I meant import. I need to import MILP. And in here, I can call it. So the result comes from calling MILP with the arguments given, which is the C, the constraints, and the integrality. Once you're done, once you have your result, you can access your variables from the attribute X. So what you'll do is, now the thing is, even though these are integers, they're actually floats. So what you'll do is you'll round them to make sure these are integers, so that when you sum... No, wait, what am I saying? No, you don't need to do it. You can sum the whole thing, and in the end you convert it to an integer. That's fine. So the total is incremented by the sum of the results in X. And once you're done, you return the total. So now let's print part 2 of the machines that you get from parsing. Now let's see if I got this right or if I messed it up. We run the solution. We give it a second and we get 2617. Let's see. 2617. Alright, so that's it. The part 2 is also correct. And you can see it's pretty quick. I mean, I get the solution essentially instantaneously. For me personally, it's not as satisfying as solving it from scratch with my bare hands, but it works really well. Now let me know if you have any questions about this. I know this is something weird to be asking you if you have questions about this, because you either already knew linear programming or not, If you didn't, I don't think my explanation was enough for you to be 100% comfortable with what's going on. Yeah, it looks like black magic. Well, it kinda is, because the actual work is being done by the function MILP, which we do not understand. I just called the function. So here, it really is just a matter. So for me, it was a matter of figuring out that I could write the problem in this neat way and recognize that this is a well-known / common problem in computer science, and there are lots of good tools to solve them, like SciPy. But me, Rodrigo, this human being, I didn't really solve the problem myself. I mean, okay, let's not go into the philosophical debate of whether I solved it or not. It kinda is black magic because I'm leveraging a function that's doing all of the work for me. Yeah. So for me, the only work was making sure I get the inputs in the format that the function expects. Alright. Well, for folks that are interested, I do recommend that you take a look at... I'm confused, what time is it? Oh, okay, sorry, because I had just seen the time, but I misinterpreted it. So do take a look at linear programming if you're curious about it. Again, it's a classical problem in computer science, and there's no very efficient algorithm to solve it in the general case. So in general, the function MILP has to run an algorithm that isn't necessarily super efficient. It's just that SciPy is fast because it's very well optimized and it's very clever. And yeah, I think we'll call it a day. I took some time to explain this formulation, or to try and explain it, so I don't think it makes sense to look at day 9 part 2 for 7 minutes, which is how much time we have left. So I'll give you 1 more minute to ask any questions live if you have them and if you want. Otherwise, thank you so much for joining, and we will be back tomorrow at 5 p.m. UTC to solve day 11, hopefully without resorting to SciPy. But we'll see. We'll see what Advent of Code throws our way. Thank you very much, folks. Thanks for joining, and I'll see you tomorrow. Bye.